So I'm Lynn Orr. I would like to add my welcome to all of you here. It's a great pleasure to see lots of old friends and some new faces as well. So my job this afternoon is to be the moderator for this session. The three speakers are all ones that I know well. They are either, we've all worked together in lots of ways over the years. We've agreed that we aren't going to tell stories about each other. And I have lots of material on these folks, but they have lots of material on me too, so we can't do too much of that, and I don't want to take much time. So look, we're going to start first with Chris Edwards. Chris was the deputy director of GCEP when it first started. He played a hugely important role in helping think through how it was going to be organized and what we would do and all of that kind of stuff. And he has been an investigator a number of times for us in GCEP efforts. He works on advanced combustion, and his talk today is going to be about ultra-high efficiency engines.
Okay. All right, that's the right screen, that's the wrong screen. I will ignore that screen. Hi. Welcome to the first talk of the afternoon session. I'm Chris Edwards. I'm the person who does the talking, and all the graduate students there, they're the ones who do the real work. So, can we move ahead? There we go. High efficiency engines. What do we mean by ultra high efficiency? I know that sounds like a marketing word, right? It kind of is. My definition of that is you have to be over 50% exergy efficiency, right? And what that would mean for a hydrocarbon is 52 or 53% on a lower heating value basis, right? I'm not really interested in anything that's below that, because that's the point at which I think we start to do things that are reasonably good. And for things below that, I think industry can do that. They have the right sort of paths. Lots of things that you got to do to get that stuff right. It's a hard thing, but we're interested in the high stuff. In order to be able to do that, there are a couple of things that you have to do. The first thing is you got to manage the exergy of the resource, and that really means you got to make sure that you don't destroy it inside the engine. You have to arrange a system that allows you to extract it in the form of work, and you need to not transfer it to the environment. Can you put it on this computer? Because I don't have my glasses on, and so it's really hard to see over there. If it's not possible, that's fine, I'll figure it out. Okay, and then the thing that goes along with it and what relates to the title in terms of integration, I can't even see the next line. Optimization and realization, I should know it, I made this. Integration is what you do when you put things together in order to make a sensible system. Optimization is trying to go one step further, and it's the one step further of not waking up in the morning and being brilliant and saying, aha, I know how to integrate this and how to make this system really good. How do you let the physics and the mathematics do that for you? And I want to touch on that because we've made some headway on that over the years. And then realization is the last piece. It's fine to do lots of analysis on these things, including state-of-the-art figures of merits and limits and all that good stuff, and put together clever systems. But the other thing is you got to actually make this stuff. And so one of the things that we try to do is we try to pick off the things that are really hard, and we try to attack those to show people that those are not showstoppers, that in fact you can make this and turn it into a reality. So all three of those pieces. The place where we're going to start, this is interesting, is looking from the point of view of energy in traditional engines. So there are three engines here: a gasoline, a naturally aspirated engine, sort of typical, best of today. Maybe I can talk while you do that. I'll get closer to this, that will make it easier for me. So think in terms of something kind of like the engine in the Prius that's running right on top of its peak efficiency, so about 37% lower heating value. If we move to a naturally aspirated diesel engine, right, we can go a little bit more efficient, where we're up at 44%, right, in terms of lower heating value. If we put a turbocharger on there to just put enough boost in to get back to the same power density or the same BMEP as the SI engine, we're at about the same. But this isn't actually the view that you want to take. You want to look at this from an exergy point of view. Still not there. From an exergy point of view, it looks a little bit different. So the first thing you'll see is the really bright, I guess magenta section up at the top. That's the loss of exergy. You know what exergy is? It's the work potential of a resource. Okay. It's the loss or the destruction of exergy that comes from doing combustion if you do the combustion perfectly. It's due to entropy generation in an unrestrained chemical reaction. Do it perfectly, complete combustion efficiency, adiabatic, all that stuff. Any heat losses down in the heat category inside of that, you still destroy about 20% of the potential of the fuel to do work. But people just normally write that off. And it's part of the reason why people don't think about really high efficiency. They say, I can't even get it, why should I think about that stuff? So that's one part of it. If you look at the rest, then you'll see that we really have three things that are key. The first is heat loss, the big green section in there. Second is that combustion loss in order. And the third is that exhaust loss, and you'll notice that the loss of work from the exhaust is actually the smallest of those three, right? And the biggest one of those is heat loss, right? And this is something that, again, we tend to accept. Big push in the 90s in low heat rejection, what were called adiabatic diesels for a while, then we changed the name to low heat rejection for that, but it was kind of tricky for a number of reasons. But it's time that we look at this again. Part of the reason for that, are we set? Great.
You have this stuff, right?
You don't worry about it. If we think about this with respect to heat loss out of the system, one of the things that people talk about is, well, I could put thermoelectrics on the cooling jacket. That's not a great idea because the temperature is relatively low. And sort of a factoid that will help you to think about this, 50% of the destruction of exergy that occurs with heat transfer is in the thermal boundary layer inside the cylinder. So of that 22% on the one that's to the far side over there, only 11% actually makes it to the wall, your first opportunity to do anything because of the destruction going from the core gas to the temperature of the wall, right? So we really need to do something a little bit different. What can we do? It's heat transfer. Heat is a transfer of energy due to a temperature difference. I only have two choices. I either bring the peak temperature down on the gases. That's the theme for low temperature combustion, a major area of research right now. Or I bring the temperature of the walls up, which is the idea of low heat rejection, and in particular thermal barrier coatings. If I look at it from the point of view of combustion, the second biggest loss that's in there, combustion is really a tricky one because there's only way to go after combustion losses, only one way to do that. You've got to do the combustion at the highest energy density you possibly can. This is something that we proved in our first GCEP work. You can actually take half of that back, but to take half of that back requires an effective compression ratio of close to 100 to 1. Right? To get a good fraction of that, you're sort of in the 60 plus compression ratio, so it's a little tricky to do. Otherwise, the only other thing you can do is to not use unrestrained chemical reaction. You've got to use a restrained chemical reaction. And the only thing that we know that uses that, the only thing that we've realized well, is a fuel cell for that. When I look at the third one, the exhaust loss, that's really a matter of integration. It's how do we go after that? How do we take that work from that system and make sure that we use it? Okay, so observation for this. The only approach that minimizes all the losses is to go high temperature combustion, low heat rejection, and either additional work extraction or regeneration. To either put another system that takes work from it or to put that energy back into the system to improve the overall extraction of exergy. And the low temperature stuff that's going on, which is just great. I've done lots of low temperature combustion stuff, is fine, but it increases combustion irreversibility because it's a dilute strategy. Right? And anytime you mix something into it, you increase the entropy that's generated for the system. And it reduces power density. And that's the one that we just haven't been able to get around because it's a dilute strategy where we use that to bring the peak temperature down inside the system, which means you can't use it at full load, right? So you have to have a power plant that's going to produce a lot less work if you're going to do it. Those things offend me because engines are there to do work. Okay, so if I think of this idea of integration, what we're going to do is take a bunch of pieces of things that already exist and we're going to integrate them together. If you look at the upper left, you see a cartoon of a piston cylinder. That's got thermal barrier coatings on it. And this is something that we've put on many of the parts in the engine. We don't have everything covered yet. We're still sort of testing that out. But basically, we've taken coatings out of gas turbines, the same thermal barrier coatings that you have in a GE gas turbine, 8YSZ, spray that on, about 1.5 millimeters thick. And if you do that everywhere except the sidewalls, if you don't do it on the sidewalls, which is where you need the oil, where you need cooling, where the rings go, all that good stuff, leave that alone, you can cut the heat transfer by 50%. Turns out most of the heat transfer is not on the sidewalls. It's up at top dead center where the temperature's high, the convective coefficient is high. That's where the big heat flux is. Don't mess with the lubrication, don't mess with the rest of the system. But it allows you to take about half of that back. In terms of extraction, the cartoon on the lower left has three things that we routinely do. If you're looking at a diesel engine, we routinely turbocharge that. If you're going to put low heat rejection surfaces on it, where the surfaces, the whole idea is to get that inner surface fiber really hot, you have to pressurize, otherwise you kill volumetric efficiency. So you will just automatically do that. But that also begins the enthalpy extraction in the exhaust, or the exergy extraction from the exhaust. You can buy today an engine that's turbo compounded that has an additional expander from it, which will take you all the way down and produce additional work. Available on the market, it's been on the market for a couple of years, turbo compounded engines. You can also buy an engine that has an Atkinson-like linkage, an actual overexpansion engine, 1.4 times the expansion ratio is compression ratio. Honda makes them for stationary power. It's called an X-Link. So if I just play cards that we have already and begin to integrate these pieces, this is what we get in the exergy bars. And if you work your way along, the one that's on the left is turbocharged with low heat rejection surfaces. If I then go to turbo compounded, I'm moving to the middle one. And if I move all the way to the far right where I'm doing the complete expansion, overexpansion, and the turbo compounding in it, then I'm getting to the point where I'm close to 50% in exergy efficiency. So my point is, just by being a little bit smart and by integration, we can get to 50% exergy efficiency, 52% on an LHV value. Notice that the power density is more than double. It's maybe a factor of 2.5. So we're building a powerful engine. The surface temperatures are essentially the same as what you have for inner surfaces in gas turbines. We're talking about 1000 C. This is not an unusual thing to do. We're applying something that's already been done. And there's still more exhaust exergy available. We haven't mined it out. What we've actually mined out is everything that you can get by expansion. But there's still thermal exergy in there, which we need to go at in a different way. We can do that too. So if you look at what people have been studying for very high efficiency engines, if you're GE, they sell an organic Rankine bottoming cycle, which you can get on one of the Jenbachers. Cummins has been looking at a steam cycle to go on their truck engines. Honda just announced that they're looking at steam bottoming cycles, Rankine cycles. I can't wait to see how that packages in a Civic. I can't really imagine how that would go. But whether you do it by the cartoon that's at the top, which would be a bottoming cycle, we actually kind of like that because since we're running our temperatures up very actively inside the system to reduce the combustion irreversibility, you can actually do that with water. You don't have to do it with an organic Rankine fluid. Or whether you do something like steam injection, which is the bottom system. Those that know gas turbines know that steam injection is often used for power augmentation, not just for NOx control. We like that too because it helps to bring the temperature down during combustion. You can phase auto-ignition processes. There's lots of good things that you can do if you're willing to do steam injection inside the cylinder. But the basic idea is you can now get to 60% efficiency or 63% on a lower heating value basis, which is what we're after. The power density we're talking about is triple the power density for this, so we're not trading it off. We're still talking about the same surface temperatures for thermal barrier coatings. The thing that we need is we need a strategy for high temperature combustion. That's the key. And if we look at that, I mean, the thing that will immediately come to your mind is, well, diesel, we've done that forever. But why don't we get to use diesel at high temperature? Soot and NOx, right? What do you do with the soot and what do you do with the NOx for that strategy? So let me ask, what if you can make a diesel engine that didn't produce soot? Now, I'm not actually going to convince you it produces zero soot. I don't believe in zeros. I do believe in something that is low relative to the regulatory limit, whatever it may be, something that would be considered negligible. What if you could do something truly crazy and take a diesel engine and instead of stopping it at 0.7 equivalence ratio where the soot normally goes through the roof and combustion efficiency plunges, what if you could run it all the way out to stoichiometric where you use a three-way catalyst? Three-way catalyst is what we use in all of our cars today. They're very cheap, very effective for reducing NOx and oxidizing CO and hydrocarbons. If you could do those things, and I admit they're a little bit crazy, but if you could do those, the result would be ultra efficient, powerful, clean, and here's the hook, possibly less expensive. Okay? And it would be very well adapted to heavy-duty transportation, which to me is the big thing that we don't have an answer for. I look at light-duty and I see all kinds of electrical things happening, whether it's hybrid or batteries or whatever else. I'm excited about that stuff. Heavy-duty, I just don't see options that I think are great. I see options that are lower power density or higher cost or tricky fuels. I think we need more options. Let me explain the possibly less expensive part of this thing. The place that comes from, I've just put out all these devices there. How could that possibly be less expensive? Interesting conversation with Craig Brewster as a VP at PACCAR, which is the parent company of Kenworth and Freightliner. So I was looking at one of their 12-liter engines that go in their big long-haul trucks. And he explained to me that the engine itself, their 2013 engine, the one I have in the lab, the engine itself is $25,000. The after treatment, the diesel particulate filter and the SCR system is $15,000. What I'm proposing is to swap that $15,000 for a $1,000 three-way catalyst system and put the rest of the money into making this system efficient. May be crazy, but that's where the possibly less expensive comes from. Okay, so in terms of trying to realize this, you know, great imagination, Chris, could you make a sootless diesel? Now, fortunately, we have this extreme compression device over here that GCEP built and we've used to explore all kinds of stuff. And what you have for the pictures, the upper one on the right is a single plume from a diesel injector, and you see it's bright yellow. It's producing soot like you wouldn't believe. Lots and lots of radiation, lots and lots of soot coming out. And right down below that, we have a configuration that's the same compression ratio. It's a 44:1 effective compression ratio, and it's not producing any soot, at least not enough that you can see if you image it in the same way. How might you do that? Here's the easy way. You do a methanol or an ethanol diesel. This is actually not a new thing at all. The data that's in these two plots, I did in the late 80s. I did it in the late 80s just kind of for giggles, in that in looking at diesel combustion, I wanted to make the point that high octane fuels that people said should never go into a diesel engine, it's just a matter of what the temperature is. This is just an Arrhenius kinetic process, and I can shift that up and down, and I move the domain. And one of the conclusions from that really early stuff done in a combustion bomb was that if you get the temperature up over 1100 Kelvin, methanol and ethanol become beautiful diesel fuels. They are absolutely wonderful as diesel fuels. Right? And so that's really what these two plots say, is if you choose 2 milliseconds as an ignition delay, it says 1100 Kelvin. I would prefer maybe 1200 Kelvin, so I have a nice fast ignition process inside of it. The two images down at the bottom, I want to make something really clear. Methanol and ethanol do produce soot. So people have talked about dimethyl ether doesn't produce soot, methanol doesn't produce soot. These do produce soot, but it's whether they produce net soot. Now the difference between these images and the one on the previous one is they were set up to image conventional diesel. And so the sensitivity wasn't very high, you couldn't really see it. This is set up so that you can really see any luminosity emitted broadband that comes from soot. And methanol and ethanol both make soot. This is reagent grade, this does not have castor oil in it for lubricity or any of those things. So you still have to be very careful in how you manage this, right, and understand the chemistry. That's what Greg Roberts is doing as part of his PhD. Not just the alcohols, but how to carry this into hydrocarbons and other fuels too. So that's the first thing. So temperature over 1100 Kelvin required for this thing. Methanol and ethanol both produce soot from this thing. But the question is going to be, sorry, I can't see, is it below the legal limits? That's the thing. Is it really sootless? And so if you want to know about that, sootless in alcohols, you got to go to an engine. So what we did, the table that's over to the left is just some of the modeling again, but it's if we did different configurations of thermal barrier coatings, of boosting, of intercooling, what temperature would we get at the time we do injection? And the answer is that we can make the temperatures we need really without any problem. And we're going to do that anyway for reasons of efficiency. So because we've gone for very efficient engines, we already have what we need to be able to use the alcohols as diesel fuels. To the right is our research engine. The way that we synthesize something like turbocharging is we use a combination of boost and heating to actually do it synthetically. We calculate what the conditions would be after the turbocharger. You can't really put one on a single cylinder research engine. And we vary the compression ratio and the valve timing and the injection and all that good stuff. The geometry we use, we took straight out of a Volvo D5 bowl and piston geometry and a Bosch piezoelectric injector. And then we measure the emissions, we measure the performance, and most importantly, we measure the soot. And the answer to the question down at the bottom is not only can you run this in a diesel, as long as the temperature's high, it makes a very nice diesel fuel. This is a plot of methanol and diesel, but you'll note that the diesel goes up, particularly around 0.6, 0.7, becomes really high. In that bottom corner is where the current standard is for diesel, right? And you'll see that the methanol is way low. Let's blow that up. If we take a little bit better resolution, now you've got methanol and ethanol on there. We've gone up in resolution by a factor of 100, so we can actually see the methanol and ethanol in the diesel range, so below about 0.7 equivalence ratio, is an order of magnitude below the standard. But here's the interesting trick. If we push that out to stoichiometric, we're still below the standard. We're a factor of 10 below with methanol, we're a factor of 2 below with ethanol. That means that we can push to stoichiometric, and we can use a three-way catalyst for the NOx. The question that's left is, can we handle the combustion efficiency? Because we need to actually get the air and the fuel together for that. That's the measurement on the right. This is not inferred. We measure the hydrogen, we measure the CO, we measure the hydrocarbons, we measure any species that contains bond energy in it, and we compute it. And you'll see that it's at 96%. That we can handle. If we take that and we roll it back in to the overall system, and we put a catalytic reactor either before or after the first turbo to finish that, a three-way catalyst to handle the NOx, and use our 96%, we had actually modeled what would happen at 100, at 90, and at 80. And what you'll see is that at 96% combustion efficiency, we still think we can do this with a 59% exergy efficiency, or 62% based on heating value, NOx controlled by three-way catalyst, and either methanol or ethanol as being the fuel for the system. So in our idea in terms of sootless diesel, this is sort of the low-hanging fruit. Okay, I'm not going to say anything about optimization because we would have to fly through that. I think I have 1 minute left. Is that right, Lynn? About 1 minute? Okay, so let me go to just our last idea on this. And that is the idea, if you're going to go over 60%, and we really can't do that by doing that with piston engine technology and combustion, because there's nothing left to milk in terms of the exergy, then we either have to go to extreme states, so 100 to 1 plus compression ratio is a very tricky thing, or we need to go to mixed electrochemical combustion systems, and that's what we're beginning to do. And so this is something that we've just been working on now, where what we're really trying to do is to use the piston engine as a pre-reformer by running it grossly rich, either in SI or HCCI mode, then pass the CO and hydrogen on through a shift reactor to a high temperature PEM. There's actually a beautiful match between HCCI run very, very rich, a shift reactor, and a high temperature PEM, the ones with phosphoric acid doping, not a low temperature PEM, not the water-based PEM. And then because fuel cells don't like to finish at high utilization, we pass that back into the cylinders to finish off the combustion process. It's a tricky kind of interleave, but as far as we can see, it's the only way at small scales. At big scales, you could do SOFC gas turbine combinations, no question about that. But that at small scales, you could build a plant that has the potential to get to 70% efficiency, and that's our next goal. So let me just flip ahead. Thanks for listening. Don't forget to visit the posters and to meet the students who actually do the work. Thank you.
Time for a couple of questions. So,
How do all these modifications and improvements affect CO2 emissions? Okay.
So it goes with the efficiency. So if you're efficient, you use less fuel for the same amount of work, that's the CO2 savings. So the attack in terms of CO2 abatement is be efficient as you can. Yep.
Yeah, so why the high temperature PEM? Are you worried about durability or cycling transients versus a high temperature SOFC?
So the high temperature SOFC is just fine, and in fact, all the stuff that I flipped through because I took too long, in that there's two branches. The HCCI one tends to match nicely with high temperature PEM, which is about 170, 180 C, right? So that's sort of nice. If you do the SI one, it has the nice characteristic that you could post-reform fuel because you're up at around 800 C, or 1,000 Kelvin or so, so you can put additional fuel, do it, and then go into an SOFC. So that's another branch that's also well worth looking at. A little trickier in terms of how to do, but both have potential. Absolutely.
thank you very much, Chris.
Okay.
Okay, well, in line with this theme of working on carbon-based energy systems, our next talk will be by Gary Mavko. Gary's a professor in the Department of Geophysics. We've also worked together for many years, and there's some shot that I might actually understand the next talk because it has to do with how fluids flow in the rocks in the Earth's crust. His topic today is linking chemical and physical effects of CO2 injection to geophysical parameters. Thank you, Lynn.
Okay, thank you. So this presentation today is focused on the problem of storing CO2 under the ground. And the approach, or the thing I will focus on today, are geophysical methods, specifically seismic methods, to try to be able to remotely sense what is going on in the subsurface. Our team includes researchers from both Stanford and Rice University. I'm the PI, Sally Benson is co-PI. I put an arrow by Professor Tiziana Venorio, and I wanted to call her name out because I'll be showing a bit of her laboratory work. And then our colleagues at Rice are making chemical reactivity measurements. So, what's the motivation? Well, this is the usual kind of cartoon. We have a complicated subsurface in the Earth, and we'd like to put some fluids in or put CO2 in. And there's a lot of questions that come up, or needs. One of them, of course, is to characterize the site before anything even happens, before any infrastructure is put in. So what does characterize mean? It means, for example, that the permeability is sufficient to get the fluids in, that the storage capacity is large enough to be useful, and very importantly, that there are appropriate seals to keep the CO2 in place. And then once injection begins, then we'd like to know, well, where is the CO2 going? And that's during injection, and of course monitoring after injection is finished. And then it'd be nice too if we could say something about what's the final state of the CO2 that goes in. Is it solid, liquid, gas? Does it move upward? Does it move downward? Does some of it precipitate into solids? Now, by far the most widely used and I would say useful geophysical method for imaging the subsurface is to use 3D seismic data. And of course, there are a lot of geophysical approaches. There are electrical and magnetic and so on, gravity. But seismic data offer probably the best combination of fairly good resolution in the subsurface and the ability to image huge, many square kilometers of the subsurface. Now, this is a very well-known example of seismic imaging from the Sleipner field. This is from published work, not mine. And what's being shown there, highlighted, are changes. And so if we look at the image on the right, this is a vertical section, and so we usually interpret these horizontal streaks as some kind of geologic boundary or fluid boundary. And we have these spectacular changes that were observed after some interval of injection. And this is viewed as one of the great successes of seismically imaging where the CO2 is going. But there are still a lot of challenges. Like the image that I'm showing you, the values plotted are seismic reflection amplitude, which is like an echo strength. And so echo strength doesn't sound like CO2 saturation. So if we can invert that, those reflections, then what we get is something called the elastic impedance. And that's a rock and fluid property, but it doesn't really tell us much yet about CO2. And so finally we have the need, and what I'll be talking about is how do we relate these remotely sensed images of elastic properties back to the properties of the rocks, changes in the rocks themselves, changes in pressure, changes in the saturation. Okay. Now, so our objective is to demonstrate techniques for quantitatively handling a number of issues. One of them, of course, is can we help to better quantitatively map the CO2 content from the seismic data? Can we measure fluid pore pressure? We have evidence in the lab as well as in the field that sometimes during CO2 injection, there are permanent chemical changes that occur to the rock frame, which means we could be dissolving minerals, washing away minerals, or precipitating minerals. And so we need to understand what those look like when they occur, and then can we learn to recognize those changes from our seismic data. So the conventional tool that's used to interpret seismic data or changes in seismic data interpret that for fluid saturation or fluid content, is a very well-known set of equations that were published by Gassman way back in 1951. And what the Gassman equations do is basically say, if we know the elastic properties before any fluid changes occur, so that would be part of the site characterization before any kind of injection began, then if we take that porous medium with whatever initial fluid is in there, nominally that could be the saline brine, but if it's a depleted oil field, that could be water and oil, maybe even some gas left in. So that's the original state. And what we would like to be able to predict quantitatively is if the rock stayed exactly the same, but the fluids in size change in some way, then Gassman allows us to predict those elastic properties quite well. And these are extremely well-known equations. They're used thousands of times a day, particularly in the oil and gas industry, and also in groundwater studies using geophysical methods. But the issue is, even though they're widely used, they're not always appropriate. There's some pitfalls, and we've observed these when we're treating rocks with CO2. So what does it mean for a seismic wave to see or detect some change in the pore fluid? So here's a very typical graph for us. On the vertical axis is an elastic velocity, say the speed of sound, P-wave velocity in the subsurface or in a rock. Horizontal axis is water saturation, so on the right, this would be 100% saline brine, for example. On the left, this would be the more compressible phase, and that could be gaseous CO2 or supercritical CO2. And Gassman's equation describes how do we compare those two endpoints if nothing changes in the rock other than the saturation. Now, in between, we get a fairly recognizable pattern as the amount of CO2 increases. So we start up here with water. When we first introduce a soft fluid, a more compressible fluid than water, then we often see this very rapid drop in stiffness or speed of sound. And so we would interpret the amount of decrease from that horizontal line as some indicator of the fluid content. And that there's a lot of details, but that's basically it. Do we see those velocities change? Now the problem is it's not quite that simple. Of course, problems never are quite that simple. So here's the same axes, velocity versus saturation. We start up here with water saturation at point A. And what I just showed you was this lowermost curve. And that's how people typically interpret seismic data for CO2 saturation. Now, another extreme, which is fairly well known in my community, is what is related to the scale of the saturation. If we take a rock, virtually any rock, and it has some content of fluid, so many percent water, so many percent CO2, that still does not give a unique seismic signature or seismic stiffness, because what we found many years ago is that the stiffness also depends on the manner in which those fluids are mixed. So if we had what we call very fine scale mixing, or like bubbly water, fizz water, then the velocities would tend to be low. But if we have separation such as fingering, and that's often the case when we're injecting a non-wetting fluid into a rock, then we get a very different velocity signature. And so again, if we're just measuring the velocity as an indicator of our CO2 saturation, then we can have pretty big errors simply due to the manner in which the fluids are mixing inside the core scale. And I should say, Sally Benson for some years now has been doing some great imaging work in her lab to try to visualize and understand that fine scale mixing. And then finally, one of the things we're looking at is, well, what if the rock itself changes? Right? Gassman and everything I've set up till now says that the rock is inert. We have this elastic frame of minerals, and all we're doing is swapping fluids in and out. But in fact, what I'm showing you here is if by some process we were to increase the porosity by just 3%, so that's going from A to D, then the velocity would have that big drop, even if CO2 is not even there. So we can get a drop like that not from changing the fluids at all, but rather by a little bit of dissolution or removal of clay or maybe even microcracking due to increased pore pressure. So in our project, we've made some laboratory measurements to try to detect these kinds of changes, especially those associated with the CO2 injection, and then some modeling work that I'll just summarize very briefly at the end. So the experiment, although in the cartoon is simple, of course I'm not an experimentalist, but I know I'm in awe of it. We have the rock sample here. That sample is put in a vessel so that a confining pressure can be applied, and then separately the fluids can be flowed through, and those fluids could be at yet another pressure. So the confining pressure and pore fluid pressures are measured separately. And then the speed of sound or the ultrasonic wave velocities are measured over time as the rock is subjected to more and more injected CO2. Now I should say that most of the experiments I'll show you, the CO2 was actually mixed with brine, and so there was just this single phase injected. But we've also done cases where we start with a brine saturated rock and inject just CO2 gas. So as I said, during the injection we monitor the velocities of the P and S waves, length changes to the rock, and also the chemical composition of the output fluid. And here's just a few typical observations. So this is a carbonate rock with a lot of very fine micron size particles of calcium carbonate, we call it micrite. Vertical axis here is porosity. The horizontal axis, well, it's labeled the injected pore volumes, and we can also think of that as time because we're just injecting at a steady rate. So the start of the experiment's on the left, and over time we move to the right. And what we see in virtually all the samples is that the porosity goes up, and part of that is due to dissolution, and that mass can be accounted for in the composition of the fluid that comes out the other end of the rock. But there's also some mechanical changes. If we start to change the rock frame, even very subtly, then the rock can undergo permanent compaction in the subsurface. And so the net porosity change is a loss due to compaction plus the gain in porosity associated with the dissolution. And of course, if we're precipitating minerals, which is sometimes the case, then the porosity would go down. Now these are the associated seismic or ultrasonic velocities for the data I just showed you. Now the vertical axis is the elastic bulk modulus. Horizontal axis again is volume of injected fluid, or we can think of that as time. And a couple of things that we observe. One of them is that if we start with a velocity here and inject, then over time we almost always see the velocity dropping, sometimes 10 or 15%, and that's primarily associated with these permanent changes to the rock frame that I mentioned. All of these measurements are actually made on a dry rock, so the data that I'm showing you here are not the effects of saturation, they're the effects that people have been ignoring. Now, the reason we have multiple curves is as we go from top to bottom, the effective pressure is decreasing, which would normally mean the pore pressure in the rock is increasing. Now this is another limestone, qualitatively the same kind of patterns. Porosity increases with prolonged exposure to the CO2. By the way, the simple explanation, which is, well, I like simple explanations, is that basically the CO2 tends to lower the pH of the fluids that are there, the water, and that obviously would tend to dissolve minerals. And so again, we have the dissolution increasing porosity and a combination of compaction and dissolution, which would give us this net curve. And these are the associated velocities, very much like the patterns I showed you before. By the way, another thing that we observed is that not only do the velocities drop as mineral is dissolved, but the sensitivity to pressure after that modification grows. So if our goal is to, for example, try to detect pressure changes from our seismic data, then at the beginning we would have this, a moderate change in velocity or stiffness. But after the modification to the pore space, sometimes that sensitivity to pressure actually doubles. By the way, one other thing I want to mention is in the case where we took a rock saturated with brine, saline water, and then injected CO2, what we found in some cases was that we would precipitate salt. Okay, and I think that's a pretty common situation in reservoirs. And the salt precipitated where the water was wetting, so in the very thin cracks, maybe at the grain contacts. So even though most of the material in the pore space is CO2, we still often have some rim of water. And it only takes a tiny amount of precipitated mineral to drastically change the seismic velocities. And by the way, the increase of velocity due to precipitating salt could be mistaken very easily for a drop in pore pressure. They would have very similar seismic signatures. Now on this plot I have velocity versus porosity, and in the back I'm showing you kind of a database of many carbonate rocks in this case. And we have some of the in situ trends. We can think of this as a diagenetic trend along here. And then there are these, a different depositional environment where we get a different slope, and that's associated with the amount of the micrite in the rock. But the point I wanted to make here is that the change that we see induced in the laboratory, so for example, this would be the initial porosity and velocity of the rock, and then as we treat it, the data point moves down here. And almost always that observed trend that occurs in a matter of just hours or days is very much like the trend that we would see in situ if we picked up many different samples. So that's an important, very useful tool for us, because if we go to a site and we can make some cross plots of the existing rocks that we would get from a borehole, then that goes a long way towards us being able to quantitatively predict what would happen if changes to the rock were to occur. This is a plot of permeability versus porosity. By the way, this is the log of the permeability. And again, you know, we often, the small dots in the background are observed points from an existing database. And again, if the rock before any injection had a permeability here, and then with injection, the porosity increased, and the permeability increased very much. Remember, this is a logarithmic scale. This was a sandstone from the Tuscaloosa Formation, and vertical axis again is velocity, and I have a typo here. The horizontal axis is the effective pressure. So that's the overburden pressure minus the pore fluid pressure. And we usually see this kind of pattern in virtually any rock we pick up, that if we squeeze down on it, it gets stiffer. Or if we increase the pore pressure inside, the rock gets softer. Now, the open symbols are the rock before any exposure to the CO2 brine. Then afterwards, we observe a fairly significant drop. Now, again, this was a sandstone, and the mechanism that seems to be causing this was the removal of small amounts of clay. In this case, it was an iron-rich clay, and through a combination of chemical changes and physically washing away the clay, it ended up having quite a big impact on the seismic velocities. And these are just some images looking under scanning electron microscope. And so this would be the rock before treatment, before and after. And we can see examples of both dissolution and precipitation of minerals. Now, last two things I wanted to just mention are some modeling tools. So we have Gassman's equation, and we pretty much know some of the pitfalls of applying that to, say, an aquifer of some composition. What I want to mention here are some issues of scale. So these plots, in these plots, vertical axis is depth, and although you might not be able to read it, the distance between these numbers is 2 meters. So these would be measurements of the shale volume versus depth obtained from well logs. And then in the middle would be curves for density, and on the right would be the curves coming from a sonic log. So again, they're the elastic wave speeds. Now, what we see on the left is fairly typical. We have shaly intervals and then sandy intervals and shaly intervals. Very common in sedimentary sequences. And by the way, this is most often the result of sea level rise and sea level drop. So it's happening all the time. And now on the right, we have, I'm pretty colorblind, so let me just point. So these peaks to the very right are the initial velocities. These are the speed of sound in the rocks fully saturated with brine. Now that would be the detail that we could see with a well log. But if we're looking at a remote image, the resolution of a 3D seismic survey might be about the whole scale here that you're seeing. So what we would observe remotely would just be an average, something like this curve here. Now the question is, can we predict what happens to the velocities if we inject CO2 or something more compressible than brine? And physically what happens is that CO2 goes into the sand or the permeable stuff and generally won't go at all into the shale. That kind of makes sense. Now in the well log, we can model that point by point and we get a pretty accurate picture. No velocity or density occurs in the shale, but fairly substantial things can occur in the aquifers or in the sands. And we can kind of see those changes here. In the shale, all the curves are on top of each other, and then there's a separation here or here where the CO2 is able to enter. And again, we would observe this curve here. Now the problem is, and a currently used method would be to say, well, we've got our 3D seismic survey, so I observe this value. I will just apply the usual technique to that average, and what we would find is that we would grossly overpredict the change that would occur from a certain change in saturation. Or what that means is that if we observed a change in the field, we could drastically underpredict the amount of CO2 that's in the rock. And so we have found some fairly straightforward ways to take in these scale effects in a pretty simple and robust fashion. So those are in some of the reports. One final thing that I will just mention is another problem or limitation of Gassman's theory is that it describes fluid changes. And for 61 years we were stuck there, and we didn't really have an equivalent for what happens if we replace water with a mineral or replace mineral with water. And we kind of happily found a method that seems to be very accurate, very robust, and quite rigorous, that we call solid substitution in analogy to the fluid substitution. So that benefited from this kind of work. So just in summary, elastic changes are one of the most broad scale ways we can look for, or changes in seismic properties over large scales and great depths. And these velocities that we observe, or changes in velocities, depend on compressibility of the fluids, but also on the stiffness of the mineral frame of the rock. And so changes to the fluids or changes to the frame are what we see elastically. So our new models not only help us understand a little bit better what changes might occur, what trends they would follow, but also to some extent how we can quantitatively model those changes. So thank you very much.
Anybody got seismic interpretations you need done? So, Gary, I have a question.
Yeah.
So maybe I'll step up to if I don't go too way, I might be using your mic. But so in the field projects that have been out there so far, the idea of some salt precipitation in the dry out areas around the well has been widely talked about. Has anybody really tried to take that into account as they look at their estimates of saturation changes? It seems to me that that's such a big effect that it really could make a difference.
I'm not aware of anybody who really did. Of course, someone in the audience knows, but yeah, that's been largely ignored. And it can be a large effect, but also that change could be mistaken for something else, something other than the salt.
Small, it could be localized.
Could be localized, yeah, wherever that chemical change is occurring. Yeah.
Going back over here.
Can we ever extract useful hydrocarbons decades or centuries later from this deposits?
That's a good question for you.
Well, I'd say I mean, you have to put lots of energy in order to make a hydrocarbon out of an oxidized carbon. So it seems unlikely that would happen at a rate that would be usable for us.
Unless the engines become so efficient that we'll just need a little drop or two. Yeah. Okay. Thank you.
Okay, so we started this session by making some CO2 in engines. And then we thought about the possibility of putting that CO2 into rocks. But obviously there's a step missing in between those two. If you have the CO2 available in the exhaust gases coming out of the engines and you want them to end up in the subsurface, then you need to capture the CO2 in some ways and separate it from all the other gases that are present. So that's the topic of the next talk. Jen WIlcox is a professor in energy resources engineering, and her talk is carbon-based sorbents for selective CO2 capture.
Thanks, Lynn. Okay. So my topic today is going to be biomimetic sorbents for CO2 capture. And the outline is essentially looking at the minimum work associated with CO2 capture, and I'm going to go through several different scenarios to motivate why we chose to think about the application that we did, and also talk about our sorbents separated into two topics: carbon-based materials, which are the ultimate substrate that we want to use for our sorbents, and also the concept of a biomimetic sorbent. So to just introduce this, there was an article that I'm kind of bringing up here that was published in Nature in 2009. And this article was discussing how we prevent 2 degrees C of warming. And what it did was it looked at this time span between the years of 2000 and 2050, a 50-year time span. And according to this article, it says that if the cumulative emissions over this 50-year time span is greater than 1,000 gigatons, then there's a probability of warming the globe beyond 2 degrees C. If it turns out that that cumulative emissions is around 1440 gigatons, that probability is increased from 25 up to 50% probability. And so what I wanted to do is I wanted to look at the business as usual trajectories of where we're heading based upon BP estimates and projections. So if we assume that coal on an annual basis is increasing by 0.3%, oil 0.9%, and natural gas by 2.3%, it turns out that business as usual brings us to about 1790 cumulative CO2 emissions over this 50-year time span. And so what I wanted to do was think about carbon capture and storage and offer up a few different scenarios to see what kind of impacts each of these might have. So business as usual, again, is looking at all the way up to 1790. So how can we look at CCS in terms of expanding this? So if we thought about replacing all of the coal with natural gas. So replacing all of coal globally with natural gas would bring us down to by around 1,512 gigatons cumulative. Suppose that we considered to capture 90% of CO2 from all point sources. So that's both natural gas and coal-fired utilities. If we did that, it would bring us down to around 1288. So we're starting to get into that ballpark of pretty big impacts. So if we wanted to try and expand CCS and the impact even further, we would really have to tackle the transportation sector. So doing that would be, some options might be onboard capture of CO2. It might be looking at electric vehicles and electrifying the transportation sector, or there's another concept called direct air capture. This next plot is looking at combining the first and second laws of thermodynamics so that we can look at what is the minimum work required for a given separation process, whether you're separating CO2 from a power plant or whether you're separating it directly from the atmosphere. And so this again motivated us in terms of the application that we began with. And so if you look at these different scenarios, you can see that the minimum work really is correlated to the concentration of CO2 in a given gas mixture. So when you have high concentrations, for instance, in the case of gasifying coal, or even as we decrease in concentration in terms of traditional coal combustion, then lower in CO2 concentrations to natural gas combustion all the way up to direct air capture. So this motivated our study in terms of looking at the low-hanging fruit, which is essentially associated with more concentrated sources first. So we're specifically focusing on developing sorbents for point source capture and looking specifically at coal combustion and natural gas fired power utilities. One thing I also want to mention here is that I've looked at a range of percent capture versus percent CO2 purity. And what you find is that in the case of compromising on the purity, you have to be careful because the densities of these gases change significantly. So if you have to transport, or if you have to compress and transport CO2 in a pipeline, and you have, say, from these examples show, for instance, going from 80% CO2 up to 95% CO2 is significantly increase in density. So there's going to be less work required if your gas is in a more dense state. So you have to be careful when you compromise on that dilution. So in terms of the low-hanging fruit, another aspect is that we wanted to think about, from a traditional coal-fired power utility, a single 500 megawatt unit emits on the average of 11,000 tons a day. And if we think about 90% capture, that's handling about 10,000 tons of CO2 per day. So this is pretty significant scale. And there are, as of 2011, approximately 600 500 megawatt plants, coal and natural gas US-wide. So in looking at this, a lot of the studies that exist in the literature are focused on the capacity of sorbent materials. How much CO2 can they hold? But what we wanted to really focus on is the kinetics of the CO2 capture process and trying to enhance and speed up the kinetics. Because if we do that, it might mean a lower number of vessels that you might need for CO2 capture, thereby reducing the capital costs of the process. And so this is one of the questions that we asked when we started to think about the sorbent design. So to motivate this is where the biomimetic comes in. So we were thinking about this enzyme, carbonic anhydrase, which is normally present in our blood, and what it does is it binds with water or binds with this hydroxyl group on this carbonic anhydrase, which is comprised of zinc with 3 histidine groups, and CO2 directly binds with the hydroxyl group to essentially form a carbonate structure. That carbonate structure can move through our bloodstream. Eventually it ends up into our lungs, and we exhale out CO2 in that process. So there's this hydration and dehydration process that happens. If you look at CO2 dissolution in an aqueous phase, and you were to add, say, carbonic anhydrase to that mixture, you could speed up the reaction by up to 8 orders of magnitude. So this was something that we thought would be interesting if we could put carbonic anhydrase on a substrate to try and enhance the kinetics of the CO2 uptake. And this was the basis of our idea. So the substrate that we chose was carbon-based. And the reason why we thought about carbon is because of the heat transfer properties. For instance, if we look at this table, we can see in the top, you have graphene, graphene oxide, and multi-walled nanotubes. And all of these carbon materials have relatively low heat capacity, say, compared to water. So if you were to compare this to a traditional amine scrubbing process where it's an aqueous phase and you've got about 70% of that as water, which drives a lot of the regeneration costs of that process. So we wanted to look at something that might have a low heat capacity, remembering that the heat of regeneration is equal to the heat capacity multiplied by the temperature change, in addition to the heat of reaction. So the reaction required to bind the CO2. We also have to break that for regeneration. The other aspect is the thermal conductivity associated with carbons is very fast. So if you're thinking about thermal processes for regeneration, you want the heat to be able to move through these materials rapidly. And so these were the properties that we thought about that were important for carbon. The other aspect about carbon is activated carbon, for instance, is very scalable. In fact, the primary source of activated carbon is coal. And so if we can use cheap feedstocks to make this, then we can start to think about applying it to scale. So to introduce the team, before I talk about some of the results that we have, so it's an interdisciplinary mix. We have Professor Bao from the chemical engineering group, and then her student John. And then we also have Dan Stack from chemistry and his student Chris Lyons. They're primarily responsible for the material synthesis. And so again, the carbon-based part is what's been carried out in Jenin's group, and then also the surface functionality is what Dan's doing in the chemistry department. Materials testing and characterization is happening in my group, so it's very important that we understand surface areas, pore size distributions, pore volumes of these materials, and then also to be able to test them and to look at what are their capacities. They at least have to be in the ballpark of reasonable sorbents that exist today. In addition to capacity, we want to be able to look at the adsorption kinetics. And so these are things that are going on in my group specifically. And Eric Rupp, my research associate, is primarily responsible for the characterization. And then Jia Jun and Reza are primarily responsible for the adsorption uptake and also the kinetic experiments. So to begin with the carbon substrates, and again, I'm going to speak about this in a decoupled way, but what we're ultimately going to do is put these together to design the sorbent that's biomimetic with the carbon substrate. And so the materials that we're using are these polyaniline hydrogels. And the way that they look, you can see in this picture, in a series of the SEM images below, and this was based upon prior work from the Bao group. But we have essentially this polymer with this cross-linking, and that cross-linking helps to dictate the porosity and also the pore size distribution of the material, which is somewhat tunable, which was kind of the goal, which I'll talk about a little bit later. In addition, there's nitrogen groups that are comprising of this basic substrate. And we're hoping that those nitrogen groups can enhance the uptake of CO2. Although we're eventually going to functionalize the surface with zinc, we think that we could actually have some enhancement in terms of CO2 uptake beyond the zinc with the fact that we have nitrogen functionality in the material. So just to recap a little bit of the recent studies that have been carried out before our work, this is strictly looking at nitrogen carbon substrates and sorbents for CO2 capture, and then looking at the different capacities that these materials have. And this is at 25 degrees C and 0.1 bar. It's important to recognize these conditions. As I mentioned in the introduction and the motivation, we're interested in both coal-fired power utility applications and natural gas. So in coal-fired power utilities, it's 1 bar is the pressure conditions, but CO2 is only about 10 to 14% in terms of concentration. So the appropriate pressure to look at would be 0.1 bar. If we wanted to apply this to natural gas, then we would want to look at 0.4 to 0.6 bar, because the CO2 is more dilute in that system. So to look at that and compare it to the work that we've done, so far what we have in terms of what we've done is there's different sensitivity parameters. So for instance, nitrogen loading on the polymers, the carbonization temperature, the method by which we actually functionalize the material so that we can control the pore size distribution. So this is the effective carbonization temperature here. And the plots up on the right, the first one is just looking at the adsorption capacity of our materials as a function of carbonization temperature with respect to the relative pressure. And then the diagram on the right is the pore diameter. So it gives you an idea of the pore size distribution. One of the things I want to mention here is that these substrates have some nitrogen functionality, which will hopefully enhance the uptake, which is what we see. But another driving force, not just the surface chemistry of these materials, is a thermodynamic driving force. So again, depending on what the pore size is and what the partial pressure of CO2 is in the atmosphere or in the flue gas that's in equilibrium with our material, will dictate whether or not we can actually take advantage of a thermodynamic driving force in addition to a chemical driving force. So for instance, when I talk about kinetics and I talked about zinc, that had to do with the actual kinetics of the chemical binding of CO2 to the zinc. And if we have a nitrogen functional group, there might be the chemical kinetics of CO2 binding to the nitrogen. But there's another kinetic term built into the kinetics, and that's how fast the CO2 can get in and out of the pore space. And so it's the diffusion kinetics. And so if the pores are too small, it may be difficult for the CO2 to get in, it may be difficult for the CO2 to get out. So that's one aspect of the tunability of the pore size. But the other aspect is, is that you have a duality between the CO2 interacting with the surface and the CO2 interacting with itself. So CO2 has a self-interaction just like water does. And so what we want to try and do is tune the pore size so that we actually get both CO2 interacting with itself and the surface of the pore. Because if we can get the self-interaction, then we have a condensed phase, and that will enhance the uptake. So there's two driving forces that we're interested in when we tune the pore size and the chemistry of the surface. And so what we're showing here is that the enhanced capacity, which we find to be about 1.1 in terms of millimoles per gram, which is pretty consistent with what I showed in the previous slide of the previous results, and again at 25 degrees C and 0.1 bar, the same conditions. But what we find is it's this 800 degrees C carbonization temperature, which leads, if you look in the upper right, and it's the open circles, which is the second plot down. And so it's not necessarily, it's difficult to tell, but there's a pretty non-uniform pore size distribution in that second plot. So if you look at the top curve, you'll see that the primary pores are associated with very small pores. And in fact, so small that that doesn't actually help us. It may increase the surface area, but it doesn't enhance the uptake of our material. And so pore size distribution is actually quite important. It's one of the aspects that we're focusing on. So the question that we asked with just simply looking at these carbon-based substrates, how can we improve the CO2 capacity of these before we move on and actually functionalize them with zinc? And so one of the other activation processes is activating with potassium hydroxide. And so in this case, what we have before activation versus after activation in these SEM images, similar morphologies, but in the second one, what you notice is that you have some of the pores are more open and some of them are more distributed based upon just smaller particles of the material. And so what we find ultimately using this activation is an enhancement of the CO2 capacity. So now we're looking at 1.4 versus 1.1. So in this case, we got a slight enhancement. And again, we can look back at the adsorption capacities in the pore size distributions of these materials. So some recent work that we've done, this is looking at slightly higher concentrations. So now certainly not as high as you would see in pre-combustion or a gasification application. But in this case, the conditions are slightly higher. They're at 1 bar. But what we found is a pretty significant CO2 capacity of 6.1 millimoles per gram. And at those conditions of 1 bar, so if you look at the literature, although I said the appropriate number is 0.1, a lot of the studies in the literature actually show 1 bar. So in order for us to compare our results and to see how well our sorbent's doing, we want to actually test them at the conditions that are available in the literature as well. And so what we found is comparing this material to those in the literature, our number is actually higher than what we've been able to see in the literature. So this is a promising material that we'd like to move forward with to actually functionalize now with zinc. And so now what I'll do is briefly talk about some of the results that we have with the biomimetic sorbents. So what we wanted to do in starting this is do some proof of concept experiments. So as you saw a little bit when I introduced the team, everybody's working in parallel. So we didn't have the carbons yet to begin with the functionalization of the zinc. So what we wanted to do was still move forward. So what we did is we picked silica-based substrates so that we could easily functionalize them with zinc, and then simply study those and investigate the CO2 mechanism associated with the zinc uptake. And I should mention that in addition to the kinetics of CO2 uptake on zinc, another benefit of zinc is that it won't interfere or it won't compete with water vapor. CO2 and water vapor oftentimes will compete with one another in terms of uptake on a given sorbent material. And so one of the issues that we wanted to try and tackle was looking at having our CO2 sorbent work in the presence of water vapor, which is in flue gas at about 10 to 15%, depending on if it's coal or natural gas. And so what we did is take these simple silica-based substrates that have OH groups on the surface of the pores, and then we functionalized them with zinc, and then we used atomic emission spectroscopy to get an understanding of what that zinc loading was on the surface. And so this is an example of the breakthrough curves that we've gotten. So on the far left, you see the dry. So in that case, you don't have any water vapor in the flue gas. And on the right are the humid conditions in which we're testing more realistic, say, flue gas, because we're including water vapor. And then what you can see down below is the table of actually showing the CO2 capacity as a function of dry versus humid conditions. And as you saw with the other materials before, going as high as, say 1.4 millimoles per gram at 0.1 bar of CO2, it's true that the loading of CO2 is not promising on these materials. So as is, the capacity is not a winner for these materials. But what we found exciting was the fact that the CO2 capacity didn't change in the presence of water. So we're getting a sorbent in which it's selective to CO2 over both water and nitrogen, which is a promising result. So to summarize, the work aims to develop an affordable and scalable carbon-based sorbent that covalently bonds CO2 with zinc functionalities for selective CO2 capture. And then also high surface microporous carbons were synthesized in simple-based hydrogel process with the CO2 capacity up to 1.42 for conditions of 0.1 bar and 25 degrees C, but 6.1, which is higher than we've seen in the literature at slightly higher pressure conditions of 1 bar. And these preliminary results do indicate that we can get equivalent CO2 capacities under both dry and humid conditions, which is promising. And then what we'd like to do in the future is actually bring these two together and look at zinc functionalization on our carbon sorbents, continue to make sure that we can tune the pore size distribution and better understand the mechanism of absorption, and also start to focus on the kinetics with the breakthrough experiments. And with that, I'm happy to take any questions.
So I have a question for you as well. So the conventional solvents used for CO2 separation are typically amine solvents of one sort and another. Can you compare and contrast with the solid sorbents? What are the differences and similarities?
Sure. So with a traditional absorption approach, where you have a solvent in which CO2 is being captured, and again for flue gas, it's going to be a chemical mechanism by which, so it's typically an amine, and the amine binds with CO2. And the largest cost associated with that really is the regeneration energy. And you're having to heat up all the water in addition to breaking the CO2 in the amine bond. But there's also a benefit associated with the fact that, even though I called it a limitation, the heat capacity of water, but it also means that when you regenerate over and over again, you might be able to save some of that heat and use it again in multiple cycles. But in the case of this sorbent technology, I mean, you don't have water like you do in an aqueous, but you do have the solid substrate. And you still have to heat up the entire sorbent solid substrate material in addition to breaking the CO2 bonds. And so it's I think of it as a kind of a similar issue, but it's a matter of comparing the heat transfer properties and also the heat capacities of water versus the substrates, and to try and figure out, it's an optimization of sorts, because you have to figure out how much of that heat could you recycle in an absorption process, how much do you lose, and then looking at the actual sorbent material, whether or not you get a savings because you don't have all of the water and is the sorbent. So it's kind of complicated, I think, but.
So what about the kinetics? Are the liquid solvents faster than the solids?
I would think, so in terms of, it depends on the solvent material, but if it's like an amine-based, then you have to think about the CO2 diffusing through the liquid. And CO2 diffusivities in liquid, oftentimes what happens too in an amine-based process, you're using steam for heat generation, or for the regeneration aspect. For adsorption, in terms of the kinetics, you might be able to, instead of using steam, you could use, say, a pressure swing. And then you might be able to optimize your system in a different way. But in terms of the kinetics, I think it's also tricky, but I think that it's probably faster for an adsorption-based process, because I know a PSA process is much faster than, say, a thermal regeneration process. But, yeah.
So the activated carbon material, what are the selectivity for CO2 and nitrogen?
So I don't have a number in terms of selectivity for the activated carbon, but in terms of, and I didn't show the results, but the materials are selective to CO2 over nitrogen, and the zinc certainly has a selectivity of CO2 over both nitrogen and water vapor. But if they're amine functionalized carbons and not just a charge interaction, like a physical interaction, then certainly they will be CO2 selective over nitrogen. But if it's a charge interaction, then they're going to be competing.
I have a question myself. When you were talking about the silica substrate versus the carbon substrate, you talked about in the beginning, so one of the advantages of the carbon substrate was the heat transfer, right? That you could, so I assume those are different. Is there anything else that's going to be different about them, or does the surface functionalization, does that really just cover the entire surface of the substrate, or is that something you won't be able to know until you combine the various groups?
Okay, yeah. So it's true. So in terms of what you said about the heat transfer properties, they are different. So in terms of the silica, it's more of an insulating material. And so it might be that we don't have as good of a heat conduction as you have, say, in a carbon. And so that was one of the limitations associated with that. In addition, the fact that we could potentially have scalability associated with the carbons, that they're cheap and readily available, and we can use waste materials to potentially make them, was also another driving force. But actually, functionalizing zinc on silica is much easier than functionalizing zinc on carbons. That project alone is a PhD student in Dan Stack's group. So the functionalization on top of the carbon is difficult. So.
What would be the cost and energy penalty for, say, capturing 1 ton of CO2?
So instead of per ton of CO2, maybe I'll just say what the percentage, say, of a typical power plant. If you looked at conventional technologies, so amine scrubbing, I think it's about a 20% hit in terms of the energy loss of the process. Is that right, Chris? You might know better. Okay. Yeah.
All right, well, please join me in thanking, oh, wait a minute, there's one back over here. So, we can,
So the biomimetic and like the enzymatic mimicking you're doing with the zinc hydroxide. So I think what I understood is it is going to make bicarbonate, right? So
right.
How you plan to regenerate from there?
So because it's a catalytic process, the idea is that the binding strength could be tuned. So depending on how zinc is functionalized to the surface, which is a big part of this work, is that the zinc and how strongly it holds onto the hydroxyl group is going to be important. If it holds onto the hydroxyl group too weakly, then you might get a strong carbonate formation, which would be too stable, which would require too much heat for regeneration to break that interaction. But if we could instead tune the zinc hydroxide interaction so that we can actually make it tunable so that the carbonate isn't as stable, so that we can easily hydrate versus dehydrate CO2 quickly and with minimal energy, that's the goal. So to have that not be too strong of an interaction. Yeah.
well, thank you very much.